Welcome to lecture number 30 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have done over the last 15 lectures. So, starting from lecture number 15, we started looking at the uniaxial stress strain response of materials, right. And we developed or we have studied several models that are used for modeling uniaxial response of metals, concrete and other materials. Okay. Then we have gone into section level. Okay. We looked at a cross section of a reinforced concrete beam or column or a cross section of a steel beam or column and understood how the plasticity develops at the level of cross section. But our assumption was the state of stress at every point is basically uniaxial. Okay. But in a general three dimensional body, the state of stress need not be uniaxial. Okay. So, it is a general 3D state of stress. Okay. Then the question is how yielding happens when you have a three dimensional state of stress. Okay. So, that is what we want to understand in the next few lectures. Okay. So, before I begin, let us review some of the concepts of continuum mechanics. In your undergraduate level, you have studied mechanics of solids or strength of materials, whatever name you have used. Okay. And if you are a master's student or a PhD student, you have studied continuum mechanics also, but nevertheless, it is a good idea to review some of the concepts of continuum mechanics starting at a very basic level. Okay. So, let us get started. So, first we will talk about the concept of stress. Okay. So, we understood the uniaxial state of stress that we started with a tensile test of a steel coupon, okay, where the state of stress was uniaxial primarily. Okay. So, now let us say I have a three dimensional body as shown here. Okay. This is my x axis, y axis and z axis. And this body is subjected to some forces F1, F2, F3, F4 and what not. Okay. Now, I am considering a point in the body which is let us say point O. Okay. Now, if I cut a plane passing through that point, any arbitrary plane passing through that point and cut the body into two halves, okay, then what happens? The internal forces will be exposed. Okay. So, that is what I am showing on the right hand side where I am considering the left hand cut portion. Okay. So, as you can see these green arrows are directed arbitrarily. Okay. They are showing the distribution of internal forces on the left halves. Okay. What is this n? Well, n is the unit normal which is normal to this surface. Okay. So, I have cut the body into two and then this n defines this surface which is the normal to this surface and magnitude is unity. Okay. And these are the forces that are acting, right. Now, let us discretize this entire area into small segments. Okay. So, let us consider one small segment which is centered around this point O. Okay. So, I am calling this area is delta A and what is the internal force in this small area is denoted by delta F. Okay. Note that delta F need not be in the direction of the unit outward normal. Okay. It could be oriented in any arbitrary direction, right. So, now I want to define the stress vector. What it is? It is the intensity of internal force at this point O on a plane. Okay. On this plane, how is that plane defined? By the unit normal n, right. And how is this defined? The intensity of internal force, that is called the stress vector or the traction vector, which is limit delta A tending to 0, delta F the force divided by delta A. Okay. Now, note that when we assume that this limit exists, we are actually making a continuum hypothesis, okay, that regarding the distribution of the internal forces, right. So, what is the unit of this? Unit of this is force per unit area, let us say Pascal or Newton per mm square megapascal. Okay. So, this stress vector, which is also called the traction vector, represent the action of one part on the other, right. So, if you look at the same point on the other half, you will see the traction vector is equal and opposite. Okay. Now, again I am emphasizing the fact that this T n, the traction vector, which is written in this manner, the superscript n indicates it is acting on a plane whose unit normal is little n, okay, and then this arrow indicates it is a vector. Okay. So, the direction of T n need not be along the direction of n, it is in any arbitrary direction. So, what we can do? We can write it into its rectangular components, right. So, let us say this has x component T n x into unit vector along the x axis I, T n y into unit vector along the y axis j, plus T n z into the unit vector along the z axis k. We can write it in that manner. It is a vector and I am just writing it in terms of its rectangular components, no issues, right. Now, it is convenient to express this T n in terms of stress vectors acting on planes which pass through the same point O, but those planes are parallel to the coordinate planes. That means, passing through point O, a plane which is parallel to xy plane, a plane which is parallel to xz plane, and another plane which is parallel to yz plane. Okay. And when the plane has a normal which is the parallel to x axis, then we will call that T x, just like we are saying T n, which is acting on a plane whose unit normal is n. Similarly, if the plane is perpendicular to the x axis or x axis is perpendicular to the plane, we call it T x, T y and T z, respectively for y and z. Okay. Then we can say that the traction or stress vector at point O. So, now I am cutting it with a plane okay. This is my plane, right. I am cutting it like that, and this plane is parallel to my yz plane. Okay. So, that means what is the unit normal? Well, unit normal is nothing but my I vector. Okay. And this is the force, internal force that is acting on this small area. Now, I am calling this small area delta A x. Okay. So, this area is centered at this point, right. So, similarly, as we have defined the traction vector T n or stress vector T n, we can define T x is limit delta A x tending to 0 delta f divided by delta A x, same as before, except that now the plane is parallel to the yz plane. Okay. We can take this delta f and write it in terms of its rectangular components. How? So, I can say delta f consists of delta f x, the x component, delta f y, the y component, and delta f z, the z component. So, delta f is basically delta f x I plus delta f y j plus delta f z k. Okay. So, can I now say that my traction vector, okay, or the stress vector at this point on the x plane can now be written as T x x into the unit vector I plus T x y into unit vector j plus T x z into the unit vector k. Okay. So, what is T x x then? Well, this is nothing but limit delta A x tending to 0 delta f x divided by delta A x. What is it? Well, this is the stress component in that direction and which is normal to the surface. So, hence we call it normal stress component. Okay, and we denote it by sigma x x. Okay. So, it is acting on the x plane, which is this superscript here, and in the x direction, which is that, or delta f x, the superscript, right. We can similarly say T x y is equal to limit this force divided by this area with the area tending to 0. And what it is? This is, as you can see, is tangential to this surface, hence we call it a shear stress component. And it is acting on the x plane. X plane means its unit normal is the I vector, x plane in the y direction. So, it is called sigma x y. Similarly, we say T x z is equal to
limit delta x tending to 0 delta fz divided by delta ax, okay, and this we call sigma xz acting on x plane in the z direction. So, this is in this direction. So, this is also a shear stress component. Okay. So, that means I can write sigma as sigma ij, where the first subscript denotes the direction of the unit normal of the plane on which it is acting, okay, and j is the direction of the corresponding force. Okay. For example, in this direction, in this case j is x, in this case j is y, in this case j is z. Okay. So, we can now say that the stress vector on the x plane at this point O, this is my point O, is equal to sigma xx into I plus sigma xy into j plus sigma xz into k. Okay. Often we drop one subscript and say simply sigma x into I, and then the shear stress components, instead of writing sigma, we use tau. So, sigma xy is denoted by tau xy, sigma xz is replaced by tau xz. Okay. In terms of, instead of writing this like that, we can also write in this manner that Tx is basically given by three components sigma x, tau xy and tau xz. Okay. Now, before we proceed further, let us understand or adopt a sign convention. So, what is the sign convention that we will be using? So, a phase will be called a positive phase, okay, when the outward normal is along one of the positive coordinate axis. For example, I am showing you a rectangular parallelepiped here. This is my x axis, y axis and z axis, right. So, if I consider this phase 1, 2, 3, 4, right, on this phase the normal is along the positive x direction. So, this is a positive phase. On the other hand, if I consider this phase, okay, so outward unit normal is in the negative y direction. So, 1, 2, 1, 2, 7, 8 is basically a negative y phase, right. Now, what is the convention for stress, sign convention for stress? We will call a stress component positive if it acts on a positive phase and in the positive direction of the coordinate axis. In other words, a positive force component acting on a positive phase will give me a positive stress component, or a negative force component acting on a negative phase will give me a positive stress component, otherwise it is negative. So, for example, on this plane MM at point O, I am showing you the stress component sigma x or sigma xx, tau xy or sigma xy and tau xz or sigma xz, all in the positive direction, because this is a positive x phase and all these are in the positive direction of the coordinate axis. Okay. So, now let us get back to the problem that we were discussing. So, we had a body and we cut it with a plane that is parallel to this yz plane. So, that I got the unit normal which is in the x direction. Okay. Now, how many planes can I pass through this point? Well, we can pass through infinitely many planes, right. But right now we said we want to look at this. That means, we will be passing through planes that are parallel to the coordinate planes. Okay. So, if I pass a plane which is parallel to zx plane through this, so I will be getting a cut something like that, then I will have similarly 3 more components, just like here we have 3 components. So, if I pass a plane parallel to xz and xy, for each case I will be getting 3 stress components. Okay. So, in total I will have 9 stress components, right. So, we can write them in a matrix form, right. So, Tx, the component of Tx are this, which we have already seen here. Components of Ty, which is the traction vector acting at the same point O on a plane whose unit normal is in the positive y direction. So, these are the stress component, and for Tz these are the stress components, right. So, if you see carefully, this rho represent the plane. So, this is x plane. Similarly, this is y plane and this is z plane, right. So, that is the first subscript. Okay. On the other hand, if you go column wise, then this is the x direction, okay. This is the y direction and this is the z direction. Okay. So, what do you see? To define the state of stress at a point, you need 9 stress components or you need 3 vectors Tx, Ty and Tz, right. And we require 2 indices to identify each component. One index, the first index is for the plane and the second index is for the direction in which it is acting. Okay. So, this is the matrix representation which is again repeated for convenience. Now, I am showing you on a rectangular parallelepiped here, I am showing you this stresses. So, sigma x is acting on positive x in the positive x direction, tau x y is acting on the positive x face in the positive y direction. Similarly, this is tau x z. So, if you take the positive z face, then this is sigma z, this is tau z x and this is tau z y. Okay. Let us recall that a vector is called a first order tensor. Okay. A vector is called a first order tensor and it is defined completely by 3 scalars. It has a magnitude and a direction, right. On the other hand, a scalar is a 0 order tensor, whereas the stress tensor is a second order tensor. So, what it requires? It requires 3 vectors. What is the additional thing we are requiring here? Well, in addition to magnitude, direction, we need the plane. So, there are 3 quantities that are necessary here, okay? Magnitude, direction and plane. Okay? So, that is what I have written here. Okay? So, the stress, the state of stress is given by a second order stress tensor, right. And this is the matrix representation of that. We often write it in terms of sigma ij or this in boldface sigma. Okay? Or if you are writing by hand, you could have also written it like that. Okay? Now, it can be shown that the shear stresses on adjacent faces are equal. This is called the complementary property of shear, which I am not going to derive in this course. I am sure all of you have done the derivation considering equilibrium in your undergraduate mechanics course. For example, consider the state of stress at a point. So, we are talking about this face and this face, these two are adjacent faces, right. So, tau x y, which is this and this is tau y x, they must be equal. Okay. So, tau x y is equal to tau y x, tau y z is equal to tau z y, that means this and this are equal, tau z x is equal to tau x z, that is this and this, right. This is called the complementary property of shear. So, what is the consequence? Well, the consequence, we had 9 components, right. Now, the second order stress tensor becomes symmetric. Okay. So, sigma I j is equal to sigma j I. That means, instead of 9 components, we can now worry about only 6 components and I can write the second order stress tensor in matrix form like this. So, this is symmetric. Okay. This is symmetric, right. So, we have only 6 components. Okay. So, now let us talk about principal stresses and principal planes. Okay. So, like I was mentioning, this is the body we took and through this point we can pass infinitely many planes. So, we can cut this body into infinitely many ways passing a plane through that point O. Okay. So, now I am claiming, and it can be proven, which I am not going to do in this course, that there exist 3 mutually perpendicular planes on which the shear stresses are 0. Okay. And these planes are called the principal planes, right. On the principal planes, the normal stresses have maximum or minimum values. Okay. And these normal stresses are called principal stresses. Okay. So, if I show you pictorially, right. So, let us say this describes the state of stress at a point in a body, okay, described by the 6 components, because 9 components are not necessary as we explained. Okay. Now, the same state of stress can be represented by this axis 1, 2 and 3, 1, 2 and 3, and the 3 components sigma 1, sigma 2 and sigma 3. These are the 3 principal stresses. Okay. They are denoted by often by sigma 1, sigma 2 and sigma 3. The algebraically largest one is denoted by sigma 1 and the algebraically smallest one by sigma 3. So, I can say this is a convention that we adopt, sigma 1 is greater than sigma 2 is greater than sigma 3. So, then this state of stress is identical to that where I am just writing the 3 numbers. Of course, I need to know the direction of the principal planes, which we shall derive later on how to determine the directions of principal planes. Okay. And the axis, instead of x, y, z, now these are rotated. So, we denote 1, 2 and 3. Okay. So, there are some special cases, let us talk about those. If none of the principal stresses are 0, then we call it is triaxial stress or a 3D state of stress. Okay. If all 3 of them are equal, then we call it is spherical or hydrostatic state of stress. In this particular case, any 3 mutually perpendicular axes are the principal axis. Imagine a small sphere immersed in a liquid. So, the state of stress in that sphere will be kind of hydrostatic. Okay. If sigma 3 is 0, then we have only sigma 1 and sigma 2, then it is called biaxial or plane stress. A thin sheet subjected to, let us say, stresses on its plane, right. So, that is plane stress. If sigma 2 and sigma 3 are 0, you have only sigma 1, then it is called uniaxial state of stress, which we have been discussing for so many lectures. Okay. For example, an axially loaded members. Although for beams, when we looked at cross section, we basically assumed uniaxial state of stress. Okay. With, of course, we have neglected some shear, that is okay for Euler-Bernoulli beam. Okay. Now, let us look at stress components on any arbitrary plane. We will come back to the principal stresses in the next lecture. Okay. So, let us say we are first talking about 2D state of stress, right. So, plane stress. The question is, let us say I have a body like this, right. This is my x axis, y axis and z axis, and this body is in plane stress in the xy plane. Okay. And I cut this body with a plane like that, this plane, right. And I am looking at this point O. Okay. So, the stress vector or the traction vector at that point is Tn, and this plane has a unit normal n hat. Okay. So, the question is, can we determine the components of Tn in terms of the stress components on the xy plane? Okay. So, let us see how we can do that. Of course, this we can resolve into its rectangular component Tnx and Tny. Okay. So, if I consider a small wedge here like so, if I consider a small wedge and take it and zoom it, right. So, what we see? Well, this is the traction vector Tn and these are the component Tnx and Tny. Okay. So, on this face, what kind of face is that? This is a negative x face, right. So, this is the positive normal stress sigma x, it is in the negative x direction, and this will be the positive tau xy, it is going in the negative y direction because that is a negative face. So, on this face you will have sigma y similarly, and this will be tau xy or tau yx, they are identical. Okay. So, now if you take this wedge and look at in this direction, so let us simplify this figure. Okay. So, then I get something like that, right. So, this is Tn, Tny, Tnx, and this is my unit normal making an angle theta with the x axis. That means, this angle is also theta. Okay. Let us say this length is delta s, this length is delta x, and this length is delta y. Then using simple trigonometry with this angle being theta, I can say delta x is equal to delta s sin theta, delta y is equal to delta s cos theta. Okay. So, now if I consider the equilibrium of forces in the x direction. Okay. So, how can I write the equilibrium of forces in the x direction? So, I will write summation f x is equal to 0 is going to give me sigma x into it is acting over the area that is delta y into delta z. What is delta z? Well, delta z is this dimension, right. So, this is stress times the area, right. So, this is in the negative direction. So, let us say I put a negative sign minus tau x y into delta x into delta z, right. That is for this one. Is there anything else? No, we have this one. Okay. This should be equilibrated with that. So, this is in the positive x direction. So, T n x multiplied by what is the area on which it is acting? It is acting on ds into delta z is equal to 0. Okay. So, now if you keep this T n x on the, let me write here, T n x on the left hand side and take everything to the right hand side and divide by delta s, then what do you get? Sigma x into delta y by delta s plus tau x y into delta x by delta s. Okay. So, what is this delta y by delta s? From here it is cos theta, right. So, you get sigma x cos theta and delta x by delta s is sin theta. So, you get tau x y sin theta. Okay. Similarly, you can consider the equilibrium in the y direction, in this direction, and you get that relationship. Okay. So, if I write this slightly differently by introducing this convention that the unit normal, which is unit normal to this plane, can be written as Li plus Mj, where Li is the projection of this unit normal on the x axis, M is the projection of this unit normal on the y axis, and Ij are the unit vector in the x and y direction, right. So, L becomes my cos theta, okay, and M becomes my sin theta, right. So, if I introduce this notation, so I can write cos theta is equal to L, sin theta is equal to M. So, this two written in this form, sigma x tau x y sigma y into L and M. Okay. Or we can say the traction vector for a 2D is equal to the stress tensor, which is 2 by 2 in matrix form, because we are talking about a 2-dimensional case, into the unit normal n. Okay. Now, if we want to determine the normal and shear stress components on this arbitrarily oriented plane n, what we have to do? Having established this one and this one, all I have to do is take component along that to get the normal stress and take component along this to get the shear stress. So, sigma n is basically Txn into cos theta plus Tyn into sin theta. So, now substitute Txn and Tyn from the previous slide. This is Txn and this is Tyn. If we substitute in here, this is what you get. Okay. And for the shear stress, well, we can do the same thing. So, tau n, this shear stress is this component of Tnx, which is negative in the opposite direction, sin theta plus Tny cos theta, and again substituting this, we can write that. Okay. And these two expressions, I am sure all of you have seen. What probably you have done, instead of sigma n, this you probably have written, this is my x prime axis and this is my y prime axis, isn't it? So, this leads to the Mohr circle representation, okay, for determining the stresses at any arbitrary plane, okay, including the principal stresses. So, if the components of the traction vector Tn are determined, we can easily get sigma n and tau n on the n plane. That means, the plane on which n is the unit normal, passing through, of course, that same point O. Okay. If we extend this to 3D using Cauchy's tetrahedron, okay, so this is a tetrahedron OABC. It has 4 triangular faces, OAB, OBC, OAC and ABC. The face ABC has unit normal n, okay, and the traction vector Tn, okay, with an arrow, right, and the stress components on the coordinate planes are already shown, sigma x, tau xy, tau xz and so on. If you again consider the equilibrium in the x direction, y direction and z direction of forces, you will get this relationship, which we have derived and discussed for 2D. Okay. For 3D also you will get the same thing. What is L, M, N? Well, these are the direction cosine, which is shown on the right hand side. That unit normal is Li plus Mj plus Nk, and note L square plus M square plus N square is equal to 1. Okay. So, this can be written in a short form, that the traction vector is equal to the stress tensor times the unit normal, or you can say it is the dot product. In matrix vector notation, it is like this. Okay. So, with that, let us summarize what we have discussed in this lecture. We have reviewed the concept of stress, and we discussed that you need 9 components, which reduces to 6 components to describe fully the state of stress at a point in a 3-dimensional body. Okay. And we have also derived the Cauchy's formula, which is this equation. This equation is known as the Cauchy's stress formula. Okay. So, in the next lecture, what we will do, we will introduce you with the indicial notation and discuss the principal stresses and the principal planes and how do you determine them. Okay. And then from there, we will see what happens for yielding to initiate, or how we can describe yielding in a body which is having 3-dimensional state of stress. Okay. So, this is the reference that I have used. It is a fantastic textbook for undergraduate level mechanics course, okay, which I have used in preparing this lecture material. Please go ahead and take a look, you will get benefited. Okay. With that, thank you and see you in the next lecture.